Right, in part A, we're told that m is a positive integer. What are the possibilities for the last digit of 2 to the m? So let's just write a few down. Okay, here we've got single digits. Now, when we get to 2 to the 4, obviously, 16 is going to end in a 6. 2 to the 5 is 32, it ends in a 2. And it must be, because the only way we get the units digit is by timesing by 2, it must be that it is then going to cycle. Okay, so we can stop at this point. So it cycles through 2, 4, 8, 6. Okay. In part 2, we're then asked what are the possible remainders when 2 to the m is divided by 3. So let's have a look at this. Remainders. Well, let's again look at 2 to the 1. So the remainder when I divide 2 by 3 is clearly 2. And when I do 4 divided by 3, I get remainder of 1. And then 8 divided by 3 is going to be 2. 16 is going to be 1. 32 is going to be 2. And it's again going to cycle. I'm not sure if we need any further proof of that. Is it obvious that that is going to happen? That it's just going to then go 2, 1, 2, 1, 2? I suppose it is, because as you're doubling, you're basically doubling. We are doubling each time. When I say we're doubling the number each time. So when we get a remainder of 1, I'm not sure if I'm going to write all this down, but I'm just going to say it. When we get a remainder of 1, if we double the number, we're going to double the remainder to 2. Now, when I double my number again, I'm going to kind of double the remainder in inverted commas, but that's going to become 4. But 3 then goes into 4, leaving a remainder of 1. So that is why it's going to cycle through. So I suppose if you're being like really careful, you'd probably talk a little bit about that. We're doubling the number each time. The remainder, I'm just going to write a little bit. The remainder will be 2, and then like 4, which becomes 1, and then 2, and then 4, which becomes 1. All right, that's enough. I'm just trying to explain where we got it from. And here we go. Very last part. Find all positive integer values of n, a and b, with a less than or equal to b, such that n factorial is equal to 2 to the a plus 2 to the b. Justify carefully why there are no possibilities. And then, oh, it does say in the question, it defines what n factorial is. It's just, so 5 factorial is equal to 5 times 4 times 3 times 2 times 1, and so on. So I think a good shout is to actually just look for some basic solutions. You know, if I'm explaining how I would do it now. I don't want to just give the solution. This is it. If you're looking at this question, then a good idea is just to try some different values of n. So 1 factorial is just 1. Now there's no way I can get that from positive values of a and b. 2 factorial is then 2. That's going to equal 2 to the 0 plus 2 to the 0, but again, a and b are not positive, so ignore that. 3 factorial is 3 times 2 times 1, it's going to be 6. Okay, now I can get that by doing 2 to the 1 plus 2 squared. So one possibility is going to be n equals 3, a equals 1, b is equal to 2. 4 factorial is 24. So then I've got 2, 4, 8, 16. That is again going to be possible if I do 8 plus 16. So it's going to be 2 to the 3 plus 2 to the 4. N equals 4, A equals 3, and B equals 4 is another solution. Okay, 5 factorial. That's actually 120. Look, you can see they're getting much larger now. Right, we might, first of all, just write down some of your numbers. Right, now can we get 120? Well, 128 is too big. I can only add 2 of them, so there's no way that I can do this. And here's the key thing. From then on, if I times by 6, I get 720. All the ones above are always going to be a multiple of 10. So 5 factorial and above will be multiples of 10. There's something else that's really crucial, and it kind of is hinted on in part B. Sorry, part 2, A part 2. It's a multiple of 10, but it's also a multiple of 3. So we need 2 to the A plus 2 to the B to end in a 0, and the remainder from dividing by 3 to also be 0. Okay, let's just bring parts A1 and 2 together now. So we see that it cycles through 2, 4, 8, 6. And the remainder cycled through 2, 1, 2, 1. Okay, and this is actually the crucial bit of information. So, to be divisible by 3, I'm going to focus on that one to start with. We require A and B to be one after each other, or an odd number away. So we're going to require that B is equal to A plus 1, or A plus 3, or any odd number. So 2m plus 1, for example. To be divisible by 10, well, I either need 2 plus 8, or I need 4 plus 6. Those are the only ways it's going to work. So I'm going to require B B is equal to A. So I was just like just checking that I was right here because B and A are not actually the number, they're the indice, the index. So for this to be divisible by 10, we need it to be an even number away. So B is going to be A plus 2, or there should be ors here, or B is equal to A plus 4. Basically, B is going to equal A. I don't want to use N here because I've already had N above. It's going to be A plus 2P. So these cannot be satisfied at the same time. Is enough. Basically, we can only have these two solutions from before when we didn't have to have a multiple of 3 and of 10. We can have a multiple of 3, that's absolutely fine. And you can see then that they do indeed just differ by 1, but we can't then have a multiple of 10 as well because then they have to differ by 2. So there are two solutions to this, as given above. Okay, now obviously that is the that is the hard bit to see in this question. Um, but I just want to like outline again, like this is how, I went about solving it. Just try and find some solutions for small values of n. That's just seems to be a good idea to get a feel for it. And then look for larger, looking at larger n. Um, we see that we get a multiple of 10 all the time. That's going to be there. And you could also look at the fact that there's going to be a multiple of 5 and afterwards 7. Like, yeah, that's a thing about factorials. Once you've gone beyond a certain factorial, that's it's like 13 factorial is going to be divisible by 13, for example. So you can you can use that fact later on. The 3 one is hinted at, obviously, in part 2 here, and the last digit is hinted at in part 1. So that really you can see that's going to come into it. But looking at 3 and 10 is not the only possibilities, which I'm going to talk a little bit about in a minute. But that's how I did it when I did it. I thought 10's a you know, I knew that 5 factorial ended in a 0 and they would from then on. Um, and then it's trying to show that there's like an inconsistency. But that's the hard bit. I can't really say how you would actually do that. But hopefully at this point you are happy that there are these two solutions and only two solutions. So well done for getting to the end of this question. I'm just going to quickly show you, this is the official mark scheme. They do it similar. They talk about, first of all, they say it's a difficult problem, but the A gives a hint. And they talk about 10. Okay, I'm not gonna like read all of this out. They then talk about how you could do it by looking at divisibility of 7, because the pattern remainders when 2 to the m is divided by 7 is 2, 4, 1, 2, 4, 1. Seems unlikely to go that route, but maybe you did. And again, we see that it's not going to be possible for other ones. 15. Yeah, I'm sure there's actually more than just 7 and 15 that you could look at. You could rewrite 2 to the a plus 2 to the b. Um, and finally, all I'm going to say is, yeah, Fermat's little theorem you might want to look into. I've actually not heard of the Euler totient function, but yeah, these are things that we can look at after this question to learn more about, and modular arithmetic as well. Okay, thanks.